Hello, I'm Caio and I'm going to present accelerating pulling through image column and column-to-image instructions in the DaVinci architecture. So we'll start with image to column. Image to column is a fairly popular way to implement convolution. I'm here using image to column as a broader name. It can actually be called as convolution unrolling, image to row, and so on. Image column here is a data transformation, so we'll apply that to the input and to the kernels of convolution. And for the input, you basically take each patch that you have in which a kernel would be applied, and you turn that into a row, and each kernel will become a column. And you do that for every kernel, you get multiple columns, and then you can just multiply those two matrices and you get the result for convolution. Next we have column-to-image. The name column-to-image can be used to refer to other things such as a reshape that you need when you're using image to column, but here it refers to the backward operator. So this is used during the training in the backward propagation phase, and it'll basically take the output that you got with image to column and put it back to the original shape you have it. The only difference is that since this is a backward operator, if you have any overlap between different patches, you need to sum the overlap. The DaVinci architecture that is mentioned in the title, it's an architecture for deep learning accelerators from Huawei. Here I just have a few examples of chips for AI, and here is the one that I'll be using, Huawei's Accelerators 910. So this is a chip that has it's based on the DaVinci architecture. And going into a little bit more details in the main component of the DaVinci architecture, the AI core, here we can see in this figure that it has mainly three units: a scalar one, a vector one, and a cube one. The cube unit is mainly responsible for matrix multiplication and convolution. It takes, instead of vectors or scalars, it takes small matrices as inputs. Those matrices are called fractals, and they have a fixed shape. This fixed shape is 16 by C0. C0 is a fixed length dimension that will vary depending on the data type. We also have multiple buffers. They are used as inputs to the cube, as the input to the vector and scalar unit, and so on. Each arrow here represents a data movement that is possible, and they are organized as a scratchpad memory. So every movement from buffer to the other needs to be defined by the software. The last component inside of the AI core is the SCU, which is represented by this yellow transparent rectangle here, and it's responsible for the image column and column-to-image instructions that DaVinci supports. So basically all the arrows that go underneath the SCU, they can perform image to column. So image column is a load, and while you're loading from L1 to the unified buffer, for example, you can perform an image column operation. Or from the unified buffer to the unified buffer, you can perform a column-to-image operation. The last component that is relevant to us is the global memory, which is outside of the AI core. So the chip, the DaVinci 910, it has 32 ASCEND AI cores, and the global memory is shared among them. You have a L2 buffer, a DDR, and a HDBM memory. And lastly, when we're doing convolution or any operations that uses an input that's usually described as AND-CWH, which is just describing the order in which every dimension is laid out in memory, we use a different shape in DaVinci. So we use what we call a fractal memory layout, and it's AND-C1HWC0. So here we basically split the channel's dimensions into two dimensions, C1 and C0, and C0, as I mentioned, it comes from the fractal size, so it's a fixed size dimension. For float 16, it has the length 16 too, and C1 will be the original dimension divided by C0. So how does the image to column instruction works? Here I have a small example this input is on the fractal memory layout. So we have here the height, the width, and C0. The other dimensions I'm not showing here just for simplicity. And basically the instruction needs a lot of parameters. It needs to know the height, the width, the stride, the kernel size, and so on. But besides those, we also need two other parameters, x and y, and xk and yk. So it works by first selecting the next 16 patches from the position x and y. So here we'll start on the position 0, 0, which is here, and we'll select 16 patches. Each patch here is 2 by 2 square. So we'll select 16 of them. We only have 16 in this input. From each of them, we're going to select the position x, k, and yk relative to each patch. So for example, the blue positions for 0, 0, or the brown positions for 0, 1. And then after we select those 16 elements, we're going to load all of the C0 dimension of each of those 16 elements. So by the end, one image column, as the example here on the blue ones, we're going to load one fractal of 16 by C0. Same thing for the brown ones here, we're only changing the xk and yk parameters, and so on. Issuing 4 image columns, we will load the full image here. For column to image, the parameters are the same as with image column, but instead our input will be a fractal. So we're working with the fractals that are in the same shape as the ones we loaded with image column. So here's our input, and column to image also requires that we initialize our output with zeros. And I'll explain that in a bit. So first, what we do, we need to load from our output a fractal given the parameters that we have. This will be initially only zeros. Then we need to sum the loaded fractal with our input. We'll have this as an output, and we'll store it back to the correct positions. So here we're just using the first positions for every patch here. And we need to do this accumulation because if we have any overlap between each patch, column to image needs to sum them, as I mentioned before. So here's where it does this sum and goes back to the output again. Before going to the implementation in DaVinci, we need to understand how pooling works. Here I'm going to use Maxpool, and the forward implementation is straightforward. You take for each path the max, so in this example here 13 and 19, and that's your output. But for the backward, it's a little bit different. So you start with the gradients you have that came to the output positions you had before, and what you need to do is basically take each patch you use for the Maxpool. Here in this example we have a little overlap, and for each patch separately you need to find out where the max was. So here 13 was in this position and 19 was in this one. So you do that, you find the argmax. This will be mentioned later as a mask, just so you remember. And we need to multiply our gradient to the corresponding patch. So we do that, and then we'll get here x in this position, y in this position, 0 in everything else. And finally we need to merge the two patches again. So if we had anything here, we need to sum them back. The semantic here is that we're only attributing the output that we got to the maximum elements that we have. So we only backpropagating to those elements, the ones that were responsible for the maximum. And now for how we implement pooling in DaVinci. So here we're talking about max pooling, and our inputs start in the global memory. So our input here will be loaded from global memory to the unified buffer, and that's because for now we're only using the scalar and the vector units, so we're not using the cube, and we only need our inputs to be at the unified buffer. So here at the unified buffer we'll calculate the max pooling, we'll get our output, and then it goes back to global memory. We could also save a second result, which is calculated from the input and the Maxpool, which is the mask. And I referred to this when I was explaining Maxpool. So here's what the mask is. It's basically every patch separated and with an argmax, so you know where the maximum element was. And we can do that in the forward if we're doing training. Otherwise, we can just save the Maxpool value. Now, we can do the same operation, but now using the image column load. So how does it work? We'll go from global memory again, but this time to the L1 buffer. And we do that because only from the L1 buffer we can then load to the unified buffer, but doing an image2col instruction. So the image2col instruction will happen here, and here our input will be in the shape that you get when you do image2col. From this, we'll do our max pooling from this input here, we'll get our output, and then we can store it back to global memory. And again, we can also, from those two temporary results, we can also save the mask here at the unified buffer and then store it back to global memory. For the backward implementation, we will have two inputs. So we have the mask that we just calculated before, and we'll have the gradients. And we'll need to load the two again to the unified buffer. So here are the two, our mask and the inputs. We need to multiply them as we did for the max pooling example before. And then we'll have the multiplication here is temporary buffer at the unified buffer, a temporary tensor at the unified buffer. And finally, we need to merge them. So we need to sum them back to the original shape. And if we have any overlap, that needs to get summed. And then we just store it back to the global memory, and that's our result. For backward pooling, we can do almost the same thing, but with no change at all, using Col2im. So here, the only step that is changing is the merge step. So instead of just doing that with regular vector and scalar operations, we can do that with Col2im, because that's basically what Col2im does. It just puts the shape that we had here, that is the image column shape, and it goes back to the original one, summing any overlap that we have. So we do that with the Col2im instruction, and we store it back again to the global memory with the same process. So now we have a rough idea to how to implement Maxpool with Im2col and Col2im, but why would we do that? And first of all, before I get into the results, all the implementations that we did were implemented with TVM. So TVM has its own language. You first define an algorithm, and then you define a schedule, and the schedule can change how the algorithm is run, so it can apply some tiling to it, reorder some loops. And with DaVinci, TVM is also responsible for making the data movements between buffers. So TVM in that scheduling language will do that. So here we have a few comparisons with what I just showed you. So in this one, we're using Maxpool and Maxpool with Im2col. Here we're saving Maxpool and the mask, and with and without Im2col. And here is Maxpool backward, with and without Col2im. So each graph is a cycle count by an input shape. So the input shapes here are the inputs to Inception v3. So 3 max pooling shapes that Inception uses. And the stride and the kernel are the same for everybody. Stride is 2x2 and a kernel of 3x3. So here in the first graph we have the Maxpool ones, and we can see clearly that the difference here when we use Im2col, we are always a lot faster than what we would be without Im2col. So this is the first result. The second one is similar, but we're doing an extra operation with that is calculating the mask. And the third one is Maxpool backwards. So here's also the difference by using Col2im. So here we're getting close to a 5x speed up, because we're using basically an operation that instead of using regular vector and scalar operations, we're using Col2im, which is made for doing exactly what we need here. And with Im2col, it's not as obvious to why it's better, but the next example will make it a little bit easier. So here we have a much simpler comparison and a much simpler example. Again, stride is kernel size is 3 by 3, but now we're only changing the input height and width. The number of channels is always 1, and we're going up to the tiling threshold. So we're going until we can without doing any tiling of any sort. And so we're loading everything to the unit file buffer, doing the operations we need there, and then going back to global memory. So here we have 3 different runs. One where we use a stride of 1 by 1, a stride of 2 by 2, and a stride of 3 by 3. And we're running 3 experiments. This is mainly just the Maxpool one, so what we had here in this graph, but we have an extra run. So we have this the dots here in orange, and those are basically Maxpool, but without using the Im2col instruction. I'm also doing the Im2col expansion. So I'm creating a temporary buffer that it's the input but with the Im2col shape, but I'm doing that just with regular vector and scalar loads. So we have those 3, and for the stride of 2 by 2, which is the closest to the other experiment, we can see the graphs here. So Maxpool is the slowest one. Again, we have cycle counts here, and surprisingly, even without using Im2col, we get a better performance by doing the expansion. So what we get here is that we get a better memory layout for the vectorial operations in DaVinci. So when we do the expansion, this is similar to what we have when we're multiplying matrices. We do an operation called packing. So we're basically taking a small block and reordering its layout so we can take better advantage of it. So that's what we're doing here. And when we're doing that with Im2col, we're doing that with almost no overhead. So that's why here is so much faster than the green and the blue ones. But Im2col has one problem, that is it does have some overhead, because if you have a lot of overlap between each patch, you're going to duplicate a lot of data. So when you do that for a stride of 1 by 1, first of all, you don't get too far to the tiling threshold, because our output gets bigger, so we don't get to see a clear difference as we do at the other ones. But we can see that for the smaller ones, for at least Maxpool is still the best here, because you're just not duplicating almost all your data with Im2col. And over here we have the straight opposite, which is a stride of 3 by 3. So when you have stride of the same size of the kernel, you have no overlap. So here Im2col is just changing the layout of the data, but with no duplication of data. And here again we see something similar to what we saw with the 2 by 2. And Maxpool is the worst. Maxpool with expansion stays in the middle, and with the Im2col is the fastest version. Here I conclude the presentation. Hopefully it makes some sense to why we use Im2col and Col2im here in this architecture. That makes sense because we have that available as a load, so we can do that with no overhead, and the data layout is just better for when we do that. So we can see the clear speedups, and thank you for listening.